Okay, good morning. Today we are going to, our agenda for today is we're going to do combined loading, okay? And then at 12:30 to 3 o'clock, we are, those of you that need to do corrections for term test 2, we'll do it from 12:30 to 3 o'clock in here, okay? And yeah, that's it. So today's topic is basically a combination, okay, of what you have learned from week 1 to last week or week 8. Okay. So we're going to combine everything together to analyze a real structure now. Okay. So we are going to analyze structure. So this topic is to analyze structures under combined loading. So let me show you what we have learned already so far. Okay. So we have learned that we have analyzed, so not just learned, we have analyzed normal stresses induced by axial loading, right? And bending moment. So axial loading, we did study this in week 1 and week 2. Bending moment, we studied in, I think, week 6 and week 8. Week 7 was reading week, right? So we know that the normal stress, I happen to want to pick in the x direction, is equal to px over a, right? Plus or minus my over iyy z plus or minus mz over izzz y, right? This looks familiar to all of you now, okay? So the first one, the first term is under axial loading. And the second and third term are due to bending moment. Okay. And then if we were to sketch the stress distribution, okay, if we were to sketch the stress distribution under axial loading, okay, so we have our normal stress, right? Then over here, this can be our y or z. We know that our stress distribution, okay, it is just an example, okay, looks like this, right? And at this point is equal to px over a. Okay? So as you can see, this is for axial loading. Okay? And then we have bending moment contributing to stress, normal stress x. Okay, so based on the bending moment, Okay. And then again, we have our stress X. And then our vertical axis can be Y or Z, right? And then we have a distribution looking like this. Hey, should not be an arrow. We have a distribution looking like this. Okay. So this axis over here is usually our centroid, right? This axis over here at this position, at this position is our centroid. Now the thing is this, what we realize from here, right? Axial load does not matter. The loads are what? Evenly distributed, right? Whereas for the bending moment, the maximum stress is furthest away or at the centroid, right? Stress X is equal to what? 0 at the centroid. Okay. So these are the distribution that we know already that is for normal stress. Okay. One is under axial loading. The other one is due to bending moment. Have you got this yet? No, right? Right. Then we have learned also. So that is week 1, week 2, week 6, week 8, right? Then we also have learned shearing stress, induced by the shear force, right? Okay. So we have shear, right? Shear stress is equal to By over Izz, right? Qz over T plus or minus Vz over Iyy Qy over T. So now I'm going to sketch another distribution. Okay. So now I'm going to sketch another distribution. So if I were to sketch another distribution, now in terms of shear stress, okay, and this can be your Y or your Z, and we will have a distribution looking like this. Okay, and again, at this point where Y is equal to 0, this or Z is equal to 0, this is our centroid. Right? And what we see, what we realize that tau max is at the centroid. Right? Tau max is at the centroid. Okay? Then there's another shear, okay, that is induced by torsion, okay, which we just need to apply the formula. Later on, I'll show you how. Next is the shear stress induced by torsion. So this one you have not seen before, but we just need to apply a formula. So what do I mean by torsion? is when we have a shaft that is built in and this is our X, this is our Y, and this is our Z, right? And relative to our centroid, what I'm going to draw next is our centroid. Okay. And the torque is in this direction. Okay. So this is my torque in the X direction is going this way. Okay. So it's a rotation. So the torque, it will induce a shear stress is equal to TR over J. Okay. Where T is the torsion or torque. It's in Newton meter. R is the radius of the shaft. And J is the polar second moment of area. The units is in meter for. And what's the formula? J is equal to twice of I. Okay, where I is the second moment of area. Units is also meter for. If it's in imperial, it's in pound inch, inch to the 4, inch to the 4. Okay. So this is another cause of shear stress. And if we look at the distribution, it looks like this. Okay. So this is our shear stress. And this is our radius. Right? So how the shear stress is distributed? It is distributed this way. Okay. Okay. So this is how the shear stress is distributed if I were to draw the one on top. Right? So the tau max is furthest away from the centroid. Right? The tau max is furthest away from the centroid. So now we have to combine all this now, okay, to analyze our structure. Okay. So over here, we learned this, right? We learned this in week 3 and week, I think 4 was it, and week 5. Right? So now we are going to integrate everything together. Okay. Why do we need to integrate everything together?
Eugene.
Okay. Yes.
Is that J equals 2, 1, like 21? Like
J?
yeah, J equals 2, 1. Is that 21? Or like what is that?
Where?
After 2. Like where you wrote down the meaning of the letters? The acronyms? You wrote J equals
2I.
2I? Okay. Thanks.
Okay. Where I is the second moment of area. Okay. So now, why do we need to combine everything? Right? What is the purpose? Why do we need to combine everything? Okay. So if you look at the piece of paper